Right, good morning, dear students. Welcome to this session on pre-stressed concrete. Uh, uh, so let us see load balancing concept that we have been discussing from the last few sessions. This session also we will see some more examples, and we will close this load balancing concept in this session, right? So let us see how this can be solved. A concrete beam with a single overhang is simply supported at A and B over a span of 8 meters, and the overhang BC is 2 meters. The beam is a rectangular section having 300 mm width and 900 mm depth, and it supports a UDL of 3.52 kilonewton per meter over the entire length in addition to its self weight. Question is, determine the profile of the pre-stressing cable with an effective force of 500 kilonewton. So the force P is given, which can balance the dead load and live loads on the beam. Okay. Sketch the profile of the cable along the length of the beam. So you have to find the profile of the pre-stressing cable, which is having a force of 500 kilonewtons. So the cross section given is 300 by 900. The cross section, whatever is given to you, like 300 mm and 900 mm. Okay, right? And the beam is uh, one end overhanging, so it's of a single overhang. 8 meters simply supported span and 2 meters overhanging portion or unsupported span we call. The live load is 3.52 and dead load you have to estimate based on the dimensions given. So pre-stressing force is a given data that is being written here. Self weight of the beam, cross sectional area in terms of meters I have substituted here. So you see 0.3 meters, 0.9 meters into 24 is again the gamma value of concrete. Kilonewton per meter cube will give you 6.48 kilonewton per meter, and live load is given by the question itself. It is 3.52 kilonewton per meter. So total put together it is 10. So adding these two values, you will be getting 10 kilonewton per meter is the total imposed load, right? Both live load and dead load, right? Right. Coming to the cable profile, if you want to present the cable profile, you need the bending moment value because E, if you want to get it, I mean eccentricity of the cable from the axis of the beam to know, you need to have the A value, okay, right, where eccentricity is not given here, so is equal to 0 if you take, okay, there is no eccentricity mentioned in the question. So whatever you find, A is equal to E plus E dash, okay. So where E is not mentioned 0, so EA itself is E dash value, shift of uh, compression line, okay. from the cable line. So in the other way, you are finding the cable line by knowing E dash value, which is A is equal to just by calculating M by P. Okay. So to get this M by P, you need bending moment values, salient values on this cable, right? So that we will have to find out the bending moment values. Bending moment value at A is equal to 0, C is equal to 0, that we know. So cable shall have zero eccentricity. I mean, it shall be at axis, uh, and at C also it shall be at axis. So then what you have, the other locations, you have bending moment at B you shall calculate, and also maximum in this span, M maximum in AB portion, that is also required. So now to get M maximum value, you have a procedure which you are well known uh, from your strength of materials. Okay, so first let us find the reactions. You know how to get the reactions. Okay, for this just use equilibrium equations, maybe sigma f y0 and sigma m a0. Okay, will give you ra rb values. Okay, so to get ra rb values you have to use equilibrium equations. So that will give you this RA value as 37.5, RB 62.5. Let us, if you want to have, I have an equation. So sigma MA0 if you write, okay, it is like RB into 8 is anti-clockwise. Just write it like RB into 8 minus remaining is clockwise moment which you get from the live load. So 3.52 into the total distance is 10 into 5. Okay. 3.52. Even you can add live load and dead load both. So you can straight away take it as 10 instead of doing for two cases. So 10 into 10 is a load and 10 is a total span into 5 is equal to 0. Okay, so RB is like 500 by 8. Okay, 62.5 is the RB value. So you can see it here, RB is 62.5. So to get RA value, uh, so RB is 62.5. So RA plus RB, RA plus RB is being the total load. So it is like 10 is the total dead load plus live load and 10 is the span. So total load is coming around 100 kilonewton. So 100 kilonewtons is the total load. Out of 100, if you substitute RB value, you get RA value. Remaining value is RA. So this is how we get it. And to get MB, it is straightforward finding bending moment at B. At a section, sum of all moments to the right, if you consider, you get MB value. Is like MB if you want. 10 is a load into 2 and into 1. 10 into 2, 10 is the UDL, into 2 is the span, into half of the distance is 1. So 20 kilonewton meter is the bending moment at B. Okay. and the only job remaining is to find where the maximum bending moment in the AB span and how much it is. So for that you need a little procedure to do it. So first select a section in the span, anywhere in the span at a distance x. Okay, now write sum of all moments about the section x. Okay, so that is mx value. So Ra into x, that you can see sum of all moments to the left you are writing. So Ra into distance is x. So Ra into x minus w into x square by 2. W into x square by 2. By 2 is written in terms of 0.5. So this is w value. W is 10 into x by 2. So x square by 2. Wx square by 2. So this is mx. Now to locate maximum or minimum, so dmx by dx is equal to 0 if you perform. So d by dx of 37.5x is 37.5, and d by dx of this is 5x square. It is actually 5x square. So 5 into 2x, d by dx of 5x square is 5 into x square is 2x. So 10x is the value, is equal to 0, x being 3.75 meters. So at a distance of 3.75 meters, nearly at center, because it is 4 is the center of 8. So 3.75 meters, roughly nearer to the center and to the left of the center. This is a location of maximum bending moment. So to get that value, just substitute x into this equation. That's it. So that value is 70.3. Okay, mx, right? And even you can locate where the bending moment is 0. Okay, where to cross, because the bending moment no, is going to become maximum, and then it has to cross this line, and then it has to hug, right? So that is what is required. So where it is going to cross this line. Okay, so that is this value, right? So mx is 0. When you just equate it to 0, that will give you x value 7.5 meters. So at a distance of 7.5 meters, very near to the support, it is going to cross this axis of the beam. Okay, so this is how we need different values, like we need mx value, m maximum value, and we need where the bending moment is 0. Where it crosses from negative to positive or positive to negative, something like point of contraflexure you say, and mb value. These three are required to complete the drawing of the cable profile. Okay, so now you can get the eccentricity value, or like lever arm we say, m by p. As I said, bending moment divided by p is given 500 kilonewtons. So bending moment 70.3 into 10 power 6 divided by p value 140.6 mm. So the cable shall have eccentricity of 140.6 at m maximum, and then at support 40 mm. This is 40 mm. Okay, and 0 here, cable shall have 0 and 0 eccentricity, and it has to cross at 7.5 meters. Okay, these distances are already uh, found. Okay, so this is 7.5 meters. This is 7.5 meters. Okay, so this is how you can draw the cable profile. You can see it here. So cable profile, that was bending moment diagram. Cable profile you can see with all these eccentricities. So this is a location of maximum bending moment, 3.75 meters. This is 3.75 meters, and this is 7.5 meters, and this is a support location where 40 SMCT it should have. Okay, so this is how you have to align your cable for supporting these loads effectively. Okay, this is the solution for this question. Okay, right. That was the, and also let us see this solution of this one. A beam of symmetrical I section spanning 8 meters has a flange width 250 and flange thickness 80 Overall depth of the beam is 450 Thickness of the web is 80 The beam is pre-stressed by a parabolic cable with an eccentricity of 150 at the center of the span, 0 at the supports. Okay, and live load is 2.5 kilonewton per meter. So 8-meter span it is. Right. So the question is to determine effective force in the cable for balancing the dead load and live load. Sketch the distribution of resultant stress at center of the section and calculate the shift of pressure line from the tendon center line. Right. So cross-sectional area shall be calculated from this given cross-section. That is I section given to you with all the dimensions. Just estimate cross-sectional area and dead load by this cross-sectional area multiplied by the gamma value will give you the dead load value, and I value shall be evaluated, and I by y, because of symmetry it is only zt and zb will be same. Q is given to you already, live load 2.5 and the span is 8 meters. Eccentricity of the cable is 150 at the center of the span. It is all parabolic. So in a span of 8 meters, it is parabolic, and supports 0 eccentricity. Both the supports it shall have 0 eccentricity. So 0 here and 0 here. Center it is 150 eccentricity. Okay, something like this. The parabola should go like this. Okay, but the cross section is I section. Okay, right. So working out for dead load and live load bending moments, WL square by 8, WL square by 8. So total moment is this much, and the tendon force is P. P is the force, tendon force. So for balancing the load, the bending moment should be equal to P into E, as we have initially load balancing concept where we had a discussion. So P is coming out to be 217 kilonewton. So moment from pre-stressing shall be equal to bending moment from the dead load and live load. This is a concept where it is applied. Now to find the resultant stress, it is like P by A. Direct stress is 3.44. Pre-stressing force divided by cross-section area. So M by P, if you see, A is equal to M by P. It is like bending moment divided by P value is giving out 150 which means pressure line is coinciding with the axis of the beam. Okay, so that is why you don't have P into E divided by P E dash by Z is absent because E dash is 0, right? The reason behind that is if you take this cross section, so where the cable is here, okay, it's the CG. So it happened in this case that the compression line is passing through the center of the cross section. So you only have E value. So if this would have been above this line, we will be having E dash. So in this case, this point is on this axis of the beam. That means on this axis of the beam, the compression line is passing through this point. Hence, E dash is 0. Okay, so in the formula of P by A plus or minus when P E dash by Z, so this E dash is becoming 0. That's why only P by A you shall be calculating. That is this stress diagram finally. Okay. So that's how it is being simplified. Otherwise, no problem. You will be calculating P E dash by Z. Everything is available. Z is already being calculated. And E dash you are being calculating now. So that's how it is. Right? If the shift of the pressure line, if it is not 150 mm, then you will be having E dash value. Because the eccentricity of the cable is given as 150. Okay, E value. So your lever arm is also is equal to 150. That is how it is being matched in this case. Okay. So this is how the load balancing concept will work, and the examples, different examples. Okay. Right. From the next session onwards, we will be talking about the stresses in tendons. Okay. Right. Thank you.